Okay, as I said, we're going to do a pericyclic reaction. The one we're going to do is cyclo addition, and we are only going to do one, Diels-Alder. All right, so Diels-Alder reactions can be very useful. As far as we're concerned, they're synthetically useful. We want to make things, and ring systems are, ubiquitous in nature. And this is a way to make a ring system from very simple compounds. This is very cool. So you see I've got a 4-carbon compound here, a 2-carbon compound here, and I make a 6-carbon compound, 6-carbon ring. Wow. So their usefulness is described here. They allow a synthetic chemist to quickly build molecular complexity, and molecular complexity means functional power. These are cool. All right. So what is meant by a 4+2 cycloaddition? Can you sort of see what that means? I just implied it a minute ago. What is meant by a 4+2 cycloaddition? I think I saw once on an ACS final, ACS organic chemistry final, this sort of language here, 4+2. So not a big deal. In my opinion, it maybe should be obvious. To some of you that's going to be obvious, but take a second look at that. What is meant by 4+2 cycloaddition? All right. Look at all pericyclic reactions. Like all pericyclic reactions, the mechanism is concerted, and that means that all three of these arrows happen at once. Okay. So these pi electrons, they're shown pointing here, right? But ultimately, they're really pointing to that carbon, agreed? These are pointing to that carbon, agreed? And these are pointing to that carbon from that carbon, okay? So you can see it. 1, 2, 3, 4, 4, 5, 6. 1, 2, 3, 4, 5, 6. You see this halogen was bonded to this carbon 6, and the halogen still bonded to carbon 6, of course. Do you see that there's a new double bond being formed between atoms 2 and 3? There it is. There it is right there. Do you see that there is a new bond being formed between atoms 1 and 6? There it is, right there. It's coming from these electrons, right? Do you see there's a new bond being formed between atoms 5 and 4? There it is. Okay. So what I'm doing, this is probably the first time in all of organic chemistry that I'm going to recommend to you that you memorize the mechanism before you memorize the reaction. So the mechanism itself, I've implied that before, I think, but this one's a big deal. I have a little bit of background noise here, so please pardon me. I'm sitting in my kitchen, and I'm not alone, so I hope that's not too distracting. What do I got here? Baby, do you need to do that?
Kind of.
Did you ask Mama?
No, sir, but Mama's fine. I need this for
Okay. All right. So, pardon me. So, what I'm going to recommend is that when you're doing this reaction, I'm going to say it several times here, that you take every time you do this, you take your 4-carbon structure and you line it up like this, right? You line your 4-carbon structure up like that. You line your 2-carbon structure up like that. You number them. Watch 1, 2, 3, 4, 5, and 6, and then you make your 6-member ring. So we're going to do this several times here in this video. All right. So it doesn't matter which direction you draw the arrows in. And the reason it doesn't matter is because these things are all happening at once. It just turns out that these electron clouds are forming all at once. And it doesn't really matter if these, it's not fair or accurate to say that we've got, 2 electrons right here and their names are, Adam and Tony, and 2 electrons over here and their names are Susan and Gail, and the Susan and Gale are going to be over here. Electrons are not localized like that, and we learned that with molecular orbital theory. It turns out electrons are shared over the entire molecule. It helps to think of them as localized, and so oftentimes we do. And I say, oh look, there's 2 electrons, and I say that. I know I say that in class, but you got to be careful. It's not exactly what's happening. What's happening is there's a new cloud that's forming around this thing, and it can be described by pushing electrons like this. These are extremely reliable, these electron pushing arrows, but they do have their limitations. So the question for you is, can you draw a reasonable transition state? Draw a reasonable transition state for this. Try to do this without looking at the book. Pause the video and try to draw what a transition state might look like, including formal charges like partial charges. All right. So we said it was concerted, and since it's concerted, this there is no the energy diagram looks like this. You've got a transition state, but no intermediates. Excuse me a minute. No intermediates, and since you have no intermediates, right? This is what the transition. This is what the energy diagram looks like. So here's your reactants. Where am I here? Here's your reactants. Here's your products, right? Or in this case, product, okay? And your transition state is here. That's a good transition state. All right. So you know what these. Can I just remind you what this is all about? Some of you are gonna. This is gonna be torturous because you know this. What's this energy right here? Say it out loud. What is that energy difference? That's the activation energy, right? And what is this energy? That is the change in the total change in energy, which we typically say is the change in enthalpy. Okay? The change in enthalpy of the reaction. Now, having said that, this is not a fraction, by the way. I just said it 2 different ways. Now, having said that, what happens if we have lower activation energy? This matters. What happens if we have a lower activation energy? Lower is faster, right? Because of the Arrhenius equation. And then higher is slower. Okay? Just 1 second. I'm going to look something up here. I'm not even going to pause the video. I'm just going to look something up. Okay. Recall that I want to just review something with you here on this page. Recall that the rate of the reaction of any reaction is equal to K times, A, X, B, Y, right? Where X plus Y is the order of the reaction, A is the concentration of A, one of the reactants, B is the concentration of the other reactant. These X's and Y's could be 1, 2, 3, it just depends on the order of the reaction. K is the rate constant, right? Remember that? Lowercase k? Well, K, the Arrhenius equation says K is some frequency factor times E, right? Over minus activation energy RT, right? And can you see that as the activation energy gets really small, this is going to go to 0, right? As this gets small, your K is going to go up, right? And can you see that? There's your K right there. So as the activation energy gets smaller, K gets smaller. I'm sorry, K gets bigger, right? As EA gets, because this is an exponent, as EA gets smaller, because it's negative, K will get bigger and the rate of the reaction will be faster, right? What about temperature? As temperature gets really big, right? As temperature gets really big, then this term is going to go get closer to 0, right? Take that to infinity, this will be 0. That's going to go to 1. Then what's that going to do? Yeah, think about that. Get a piece of paper and a pencil. I think that it's better just to think of it in terms of activation energy, but you should do the same thing with temperature. And what about that changing? All right? So if you've got the energy for it, get a piece of paper out and a pencil and figure out what those things mean as well. All right? Now, most Diels-Alder reactions are thermodynamically favored, believe it or not, at low and moderate temperatures. Okay? So at temperatures above 200 degrees Celsius, the retro Diels-Alder can predominate. So at high temperatures, you see here's our Diels-Alder. 1, 2, 3, 4, 5, 6. If we're going to predict what happens here, right? We're going to make a 6-membered ring. Every Diels-Alder makes a 6-membered ring. Every Diels-Alder makes 6-membered ring. So you got to find it, right? You got to find your 4-atom structure and your 2-atom structure, okay? Now, but a retro Diels-Alder is when you take the 6-membered ring and you tear it apart, okay? And that can be done at high temperature. Okay, so the next question is, will reaction be favored or disfavored by entropy? So we've got a couple ways to think about entropy. And so I've got a couple slides here to talk about that. So first of all, remember that the free energy is got an enthalpy term and an entropy term. And typically we say dH minus T ds, right? So we're just taking that minus and putting it over here into the entropy term. So the enthalpy term the enthalpy term's got several things that play into it, but the most prominent factor is the kinds of bonds that are broken and the bonds that are formed. All right, so you have 3 pi bonds that are broken and 1 pi bond that's formed and 2 sigma bonds that are formed, and that will give us a negative enthalpy. Okay, in other words, the enthalpy of the products are lower, right? It's going to look like that. All right, but the entropy term, what is that? So in the entropy, we have not only 2 molecules that are combined with 1, okay, but we also have a ring that's being formed, and that's got less freedom to flip around. Okay, so in both of these terms, both of these factors make the product more ordered, lower entropy. The change in entropy then is going to be negative. Okay? So if the change in entropy is negative, what's the sign for the entropy term? Okay, so the sign for the entropy term is always going to be positive. Why? Because that's always positive, that's always negative, and this is negative, and a negative times a negative is a positive. Okay, so suppose that you know that then, that this is negative and this is positive. Do you expect delta G to be positive or negative? Can you see that it depends on temperature? It depends on temperature. We did this in principles too, but here's a chance for us to use it now. That the free energy change of a Diels-Alder reaction is going to depend on temperature. So, are there any other disadvantages if the temperature is too low? Any other disadvantages if the temperature is too low? And think back to that question I gave you a little bit ago. You got to get over this. This is your activation energy, right? And remember that the Arrhenius equation says minus EA over RT think low temperature. We started to do this a minute ago. I never gave you the, I'm not going to give it to you now either, but think about that. If the temperature is too low, what's the disadvantage of this to a synthetic chemist? Why is that a problem? It is a problem. All right, so now in the Diels-Alder reaction, the reactants are generally classified as a diene and a dienophile. A couple, I don't know, that's probably not a bad word, but this one's just ugly, right? Dienophile, right? It's a diene lover, right? That's what phile means, a diene lover. So if you have a dienophile, it's going to be the one that loves the, like this one right here is thinking about, this is thought bubbles. It's thinking about that diene over there, and it's loving it. Oh, I love you. I really want to react with you. Okay? So this is thought bubbles. Can you tell? All right. So the dienophile is this guy right here, and the diene, of course, is this one. If the dienophile is not substituted with an electron withdrawing group, it's not going to be kinetically favored. It's going to take a lot of activation energy. Your high temperature is required to make this reaction go forward, okay? So, and obviously if you go too high, we're gonna break this thing apart. So it's a problem, okay? It can work at about 200 degrees Celsius. Anything much higher than that, we'll see, even at 200 degrees Celsius, it's 20%. But anything higher than that, and we're not gonna get a significant reaction. All right, so what does that mean? Okay, I just threw a term in there. Electron withdrawing group. What is an electron withdrawing group? Well, it's going to be something that pulls electrons away, right? So let's look at some examples. When an electron withdrawing group is attached to the dienophile, the reaction is generally spontaneous. So if you have a carbonyl, this looks like an aldehyde, right? It's 100%. Really? Wow. Really? Wow. Look at this. Why? Well, because this is withdrawing electrons. How is it withdrawing electrons? Remember we did this ARIO? So that came out of someone's mouth in class. Which of these is responsible for the withdrawing effects? Well, there's two of them really, induction and resonance. Look at this. These guys can come here and these guys can come here. Oxygen is an electronegative element, and so this has got a resonance structure. Those are electrons, a negative, and a positive, right? So this guy right here has got some partial positive character to it. That carbon does, because this dienophile has some resonance factors. Okay. Now there's a separation of charge over here, so this is the predominant structure. However, it is an electron withdrawing group, and that's the reason why. That is the reason why. All right, so show how the groups in red are electron withdrawing using resonance and induction where appropriate. Yeah, do that. Do what I did up here, do it with all four of those structures there. Okay, so that's good. If you get an electron withdrawing group on the dienophile right there, if you get one on the dienophile, you're going to get an appreciable reaction. Okay, so there's a couple other things we need to consider about the Diels-Alder reactions, and then we'll be done. Actually, they're sizable enough that it will be a day's work. Okay, so Diels-Alder reactions are stereospecific, depending on whether the E or Z dienophile is used. So if is this E or Z? Is this E or Z? E or Z? Pause the video if you don't know. And if I could get you to look it up, you would win. You'd be better off if you stopped and looked it up. Okay, I'm going to suppose that you had your chance to pause it. I'm going to tell you now. And Gagan, Zusammen's the same side. Yeah, these are Z. Okay, can you see that? They're Z. And can you see these are still on the same side? Why is this? Because there's no it's concerted. Okay? And that means that this goes here. I forgot to number these. 1, 2, 3, 4, 5, and 6, right? This one goes here, and this goes here, right? 1, 2, 3, 4, 5, and 6. Can you see I've got my double bond between 2 and 3, right? A new bond between 1 and 6, perfect, okay? So that means that goes there, and this one goes here. And you see they're going to be on the same side because it happened all at the same time, right? It's concerted. So they are stereospecific. Okay? Now that we have that, and you can see, oh, I already answered that for you, didn't I? Should have let you stop and do that. Okay, can you see that these are not on the same side, right? So this is the E isomer. And so these two halogens are going to be on opposite sides of that ring. Okay. So why did we not say plus an enantiomer here? All right. Now, a carbon-carbon triple bond can also be reacted as a dienophile, because really the big deal is we want a pi system here. And there's definitely a pi system here, right? There's actually 2 pi bonds. Okay. So if that's the case, 1, 2, 3, 4, 5, 6. New bond being formed there. New bond being formed here. Boom. 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 But I'm only using 1 pi bond, so the other one's still here, right? And there's a new bond between atoms 2 and 3. Okay? So please stop the video and practice with Skill Builder 17.3. Label it. Label Skill Builder 17.3 and go practice with that. Whoops. Okay. All right. Predict the products for the following reactions. So I want you to pause the video and do this, and I'm going to show you. My solution. Pause the video. And then come back on and I'll work it out with you. Okay, let me suppose you paused it, and let me come and do this. I'm going to find my 1, 2, 3, 4, and I'm going to do this. First of all, I'm going to lay out my framework. Okay, I'm going to call this atom 1, 2, 3, and 4, and then I'm going to that's 1. Sorry, that's messy. 2, 3, and 4. I'm going to call this atom 5 and 6. Okay, and so here's 5 and here's 6. Now bonded onto atom 5, it looks like we've got a ketone, right? I'm going to call this X and Y. Here's atom X and here's Y. Agreed? 5 is bonded to X. X has got a double bond. Okay, good. We're good there. 6, it looks like that's got 2 methyl groups coming off of it, which I'm going to call A and B. A and B. It doesn't matter which of those is A and B. All right, now that I've done that, I'm going to count all my carbons here. Oh, I don't have I got more atoms I got to bond on there, right? So, yeah, look at that. Okay, now I'm going to count my total atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with an oxygen. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with an oxygen. Okay, good. So I've counted everything up. Now that I've done that, okay, I am going to, we're going to have a hard time with a sigma bond here, but no, it can be done. It's just going to be in the way. It's a little ugly, but it's going to be in the way. I bet you this would be better if it was flipped. I'm going to do it again. I'm going to flip this guy, okay? I'm going to keep this one the same. 1, 2, 3, 4. It's just too crowded there. Okay? I'm going to call this atom 6 and this atom 5. And I'm going to put my ketone up there. Yep. less crowded that way. Okay. Now that I've got that, I'm going to have a new bond between atom 5 and between atom 6 and 1, right? Watch this. Boom, boom. This is going to be confusing there and here. Boom, 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 boom. Okay? Now that I've got that, if this comes in from the top, this one's going to be up. And that's going to be down. Right? And that's going to be down. Okay, so let's do it. Right? I never named that atom, but here's atom 2. Here's atom 3. Now 5 has got some junk on it, doesn't it? Agreed? And this one because it's coming in from the top, right? There's my wedge. Okay, now this guy also, whoops. But this one has got one more methyl group that's going up. Wow. Wow, what a mess, huh? That's tough. That's a tough structure. Okay, now that's it for that one. I'm going to do a different color because it's getting too busy here. I know that in a retro 1, 2, 3. You see how I'm just numbering everything very carefully? 5 and 6. Okay, in a retro Diels-Alder, it was the atom between 4 and 5, and 1 and 6 it was formed. But that has an electron withdrawing group on it. That's the electron withdrawing group. I bet you this has changed. I wish I could number this. I'm going to go different color altogether. Let's go green. Will you be able to? No, green's going to be too hard to see. Let's go orange. Okay. 1, 2, 3, 4, 5, and 6, right? Because I have my electron withdrawing group. Aha. Electron withdrawing group. So that said, here was the bond that was formed, and here was the bond that was formed. Okay? And so what I've got is, and presumably, yeah, these were bonded, 2 methyl groups coming off of that. So it's 1, 2, 3, 4. And 4's got 2 methyl groups on it. Agreed? There's a double bond here and a double bond here. Okay, because it's atom 1, 2, 3. Are you sick of me counting? I'm getting sick of it. 1, 2, 3, 4. That was this guy. Now this guy over here, that was a triple bond. And then nitrile, right? 5 and 6, and on this is 6. Here's atom 5, and on 6 was a cyanide. Okay, this looks like acetylnitrile. Wow, very cool. All right, very good. Hope that's helpful. We still have some more things to consider though with respect to Diels-Alder. Let's move on. My drawings are horrible here, aren't they? Okay, so Diels-Alder reactions can be also affected by diene structure. I guess that should be obvious. We hadn't talked about it, so maybe it's not. Recall that many dienes can exist in an S-cis or S-trans. We did that in the beginning of dienes, beginning of this chapter. They can be either like this or they can be either S-cis. Where's my marker here? Let me go back to red, can I? But if we have rotation about that bond, right, then it becomes S-trans. Now, which conformation is generally more stable? We said this before, in a couple of sections ago. Diels-Alder reactions can only proceed, watch this now, when the diene adopts the S-cis conformation. It's got to look like that, which we were reminding ourselves by drawing it like that. Okay, so again, I asked you at the beginning here to memorize, and then always find your diene and your dienophile and draw them out at the beginning of a reaction and make it easier, and then number everything, right? Make it easier for you to find what's going on. So, but they have to be in the S-cis conformation. So dienes that can only exist in S-trans conformation (1, 2, 3, 4) cannot react Okay? Now, those, on the other hand, that are locked into the cis conformation undergo Diels-Alder reactions very readily. Okay? Cyclopentadiene. Take a minute and write that out. Draw that out. Please pause the video and draw out cyclopentadiene. Okay? Cyclopentadiene is so reactive that at room temperature, two molecules will react together. Really? How? Again, please grab your paper, draw that out. Two molecules will react together. Two molecules will react together. Show the reaction and the products. Okay? All right. You know what? I'm going to do the cyclopentadiene together here. I was thinking I had a picture of it here, but I don't. 1, 2, 3, 4, right? Agreed? So what's going to happen is 6, right? This is going to give us a new 6-membered ring with a bond here. But, so it's 1, 2, 3, 4, 5, and 6. Okay, because I've got all those atoms in there, but what I don't have is what, A, B, and C. So it looks like I've got a 3-atom. Oh, and also there's a bond here. I don't have this atom, X. So there's a bond here, right? There's my atom X. Can you see it between 1 and 4? And there's a 3-atom ring that goes from 5 to 6. 1, 2, 3, okay? And it's C and B, and there's a double bond between those two. That's it. Wow. Try it. Do it. You'll like it. The way I've drawn it, I mean, my markers is just ugly today, but do it. You'll like it. Very good. Okay, so now draw 4. Let's go back on to the next story, okay? Next page of the book. So draw 4 potential bicyclics with these two guys, okay? So 4 of them. 1, 2, 3, 4, 5, and 6, right? I'll call that atom X. And this, I don't think it matters if we call those whatever, CHO. You know those are aldehydes, right? Draw the structures out of those. So they're electron withdrawing groups. Now I'm going to draw my 1, 2, 3, 4, 5, 6, my 6-membered ring. I'm trying to be a little slower here. Make them pretty. 1, 2, 3, 4, 5, 6. Okay. 6 has got an aldehyde on it. 5's got an aldehyde on it. Right? And okay, all right. Now this I didn't draw the stereochemistry here, but this could be coming out, right, toward me. And if so, that might be going back behind. Or these might also be coming out, right? And that could be going back behind. Okay, so if this is going out, yeah, I think you get what I'm saying here. Okay, this is a stereo center here. That 1 and 4 are stereo centers, and they can be that carbon bridge, that one carbon bridge could be coming toward me or behind, and the aldehyde groups could be going back or forward. Okay. All right. So you need to draw all 4 of those out. Now, 2 of them are impossible. Say which ones are impossible, and say why. I think you may need to refer to the book. I might have a slide here on this. So it turns out that the terms ENDO and EXO are used to describe the functional group positions. So in the previous picture, I had this drawn wish I had a way to... With this coming out toward me, right? That's a wedge right there. Can you see that? That would be the wedge. These are the same thing, okay? And then I've got... This is the same thing, but you might like drawing it better from the side like that. Can you see how this one carbon bridge is pointing up? And can you see how these two, here's a 2 carbon bridge, it's pointing down, and one is pointing down? Can you see that? Okay. Now it turns out that the endo this endo position is the one that's, can you see this is closer to the 2 carbon bridge, this one's closer to the 1 carbon bridge. 1 carbon bridge, and here's the 2 carbon bridge, right? Can you see that? There's 2. Okay, so the endo is closer to the 2 carbon bridge, and the EXO is further from the 2 carbon bridge. All right, so it turns out that the endo is favored. All right, the electron withdrawing groups attached to the dienophile tend to occupy, watch this now, the endo position. So in that previous structure that we had, here were a couple of the products possible. So I hadn't drawn any like that for you. The way that I drew that, and this is probably better, right? If you're looking, but here you're looking, if you got an eyeball and you're looking down at it like that, then you'd see this. You'd see this structure here, okay? And then you've got this CHO going away, and CHO going away. These two are the same thing. Those two are the same. All right, so it turns out that the endo is the major product. And can you see that? You've got your electron withdrawing groups, and they're actually closer to the 2 carbon bridge. All right.